Olá, pessoal, sejam bem-vindos aqui ao canal Ricardo Felício Oficial, agora no Rumble. Se você veio do canal Ricardo Felício do YouTube, ou O Farol do Brasil, ou então do Embaixada do Reino. Hoje nós temos aí uma surpresa muito interessante. Hoje nós trouxemos para vocês a palestra do professor Jan Rutherford Plimer. Ele é professor de Geologia da Universidade de Melbourne, atualmente aposentado. E ele fez uma palestra que foi proferida no dia 24 de fevereiro de 2023, em evento do Heartland Institute, aquele famoso instituto, o qual os aquecimentistas vagabundos adoram difamar, dizendo ser financiado loucamente pela indústria do petróleo, quando esses mesmos aquecimentistas usam fábulas de dinheiro dos seus impostos para fazer o lixo de pesquisas deles, né? Temos que lembrar sempre disso. Aliás, vocês verão o anfitrião mesmo falando sobre isso logo na abertura da palestra. Entre mentes, a palestra desse ilustre professor PhD e medalhado com o prêmio Clark traz coisas muito interessantes, pois nós já falamos de nuvens aqui no canal diversas vezes e como elas são importantes para a definição dos estados climáticos. Não é à toa que o Dr. Clauser, um cientista que foi laureado recentemente com o Prêmio Nobel, bateu feio na turma da pseudociência do aquecimento global, tendo em vista que os modelos de computador do IPCC, né, aquele painel pseudopolítico científico, não sabe simular os efeitos das nuvens. Eles continuam colocando feedback positivo para aquecimento. Assim, como os famosos geólogos Maruyama, do Japão, Ian Clark, estadunidense, Kenichiro Sugio, o saudoso Sugio 01 da geologia no Brasil, João Wagner de Alencar Castro, também da geologia do Brasil, todos céticos à panaceia climática. O Dr. Jan Plimer, também geólogo, irá nos mostrar nesta importante palestra outros efeitos do planeta Terra e o seu clima, tá? As principais emissões e remoções de CO2 pelas rochas e oceanos e muitos outros processos importantes no movimento da tectônica de placas e o nível do mar. Quanto à linha do tempo, deixe de lado por um momento as suas crenças e fixe-se em algumas colocações importantes que farão sentido, de forma que você possa reter o que é bom, aprendendo mais coisas, né, com essa apresentação. Tá? Também vale comentar que o professor usará o tempo verbal, né, achei isso sensacional, na primeira pessoa do plural, indicando a ação da natureza e não dos homens, quando ele elencar as diversas mudanças ou as ações que irão ocorrer, certo? Então, eu coloquei muitos desses verbos entre aspas, porque a gente fez aqui a tradução, né? A gente colocou entre aspas para que as pessoas entendessem que se trata na visão da ação da Terra, como se fosse vamos dizer assim, um relatório proferido por um gerente. Nós fizemos isso, nós colocamos mais CO2. Ele está falando lá que foram os vulcões, que foram os oceanos, tá? E não a ação da humanidade. Foi uma forma peculiar do professor Plimer realizar as suas explanações, né, sobre as ações do mundo natural sobre o clima, sobre a atmosfera. Então foi muito interessante esse tipo de forma de colocação do professor Jan Plimer. Tá? Então está aí, aproveite essa brilhante exposição do geólogo, professor Jan Plimer. Até já, pessoal.
This is amazing. If money were a limitless resource for us here at the Heartland Institute, the way the media says it is, the way we have all the fossil fuel funding pouring in, we would have 500 speakers and this conference would go on for 2 weeks and we'd still be leaving some people out in the cold. But you know, we have to make some dividing line. Okay, we can get you in. We don't have time. Expenses being what they are. Australia is a long way away, and it's rather expensive to fly people in from Australia. We have scientists, economists, policy experts from all over the world. And as we're going through our list of who to speak and who not to speak, as we're putting this together, we heard from somebody in Australia, Dr. Ian Plimer. The world needs more Dr. Ian Plimers. Now, here in particular is the reason why. He says, hey guys, guess what? I love your climate conferences. I've been there before. I'm going to be in the United States. In fact, I'm going to attend your climate conference. So I'm paying for my own travel. If you need a speaker, I'm here. I'm ready to speak. And I'm thinking it's like Aaron Judge calling up the owner of the Yankees and saying, hey, you know, I love playing baseball, and I plan to be around Yankee Stadium sometime around opening day. If you just happen to need a left fielder, I'm available for free. The world needs more Dr. Ian Plimers. Dr. Ian Plimer is a former professor of geology at the University of Melbourne, an emeritus professor of earth sciences at the University of Melbourne, a former professor of mining geology at the University of Adelaide. Dr. Plimer has written several books. He is one of the best, as I've mentioned some of the propaganda that has been floated around that we shoot down at the Heartland Institute. Dr. Plimer is one of the best at doing the same. He has written several books. One of them that I hope he'll talk about a little bit more in his talk is Green Murder, a life sentence of net zero with no parole. It's my pleasure to introduce to you Dr. Ian Plimer.
Well, thank you for that introduction. Patrick Moore stole my whole talk, so I think I'll go back. It's only 20 hours flying. There's only one button to push and I can't get it right. This is the only takeaway you need from a geologist. You will not find any people in my profession who would claim that humans can change a major planetary system. We are not crazy. There are a number of fundamentals. No one has ever shown that human emissions of carbon dioxide drive global warming. And just perish your thought, in case I'm wrong, you then have to show that the 97% of natural emissions don't drive global warming. The foundation is absolutely and totally wrong. There are major planetary processes that drive climate change, and we have a great ego and we think we can drive how the planet works. But there are some fundamental things that we see in the history of the planet. A key question: when did it first rain? Because that was unprecedented when it first rained. Not much else is unprecedented. And we can take you to Western Greenland, show you these old gravels from running water. It must have rained. And at the same time, we find evidence of life on Earth. We have the chemical fingerprints of life. That is extraordinary, and that is unprecedented. But most of what we hear in the press about unprecedented events, they're not. They're just because people are ignorant of history. We have some great ice ages in the past. Every single ice age occurred when we had more carbon dioxide in the atmosphere than now. Every single ice age. We have 6 major ice ages. Some of them occurred when we had a bad planetary address. Some of them occurred when continents went over poles. But these ice ages are the clue to climate change. And the very first one we see is from Africa, the Pongolian at mid-latitudes. This is a debris left behind by retreating ice. And obviously the climate warmed up after that. We have no idea how this ice age started. We have no idea how it finished. And that's the fabulous part about science. We don't know very much, and it means that we have a lot more to do. But after that big ice age, what did we see? We saw colonial life. The bottom part of that diagram, we see stromatolites. These are bacterial colonies, organised. And this life occurred when the planet warmed up. And then again, we had another big ice age. This one was when the ice was at sea level, and at the equator. And the carbon dioxide content of the atmosphere, instead of being 0.04% as it is now, was at about 20%. So if you think carbon dioxide drives global warming, go back in time. This is debris left behind by retreating ice. And at the same time, when we washed out material from this debris, we fertilised the oceans, we had a diversity of life. Suddenly we started to put oxygen into the atmosphere. Suddenly we had oxidation and we had banded iron formations. And these banded iron formations are a worldwide event of oxygenating the planet. That was unprecedented, but not 3 hot days. That's not unprecedented. And this is what happens to those iron formations. They formed during very cold times. They then got beneficiated during tropical times, and here in Western Australia, they're mined in an arid climate. And they tell me that I'm a climate denier, that I don't understand climate change. So look back in the past. We have a much better story to tell. And when we look at the history of ice in some of those light blue vertical lines and the dark blue vertical lines, we've got 3 of the big ice ages here. And the evolution of this planet is tied in to the evolution of the atmosphere, the evolution of the rocks, the evolution of the oceans, and the evolution of life. You cannot only look at the atmosphere, and that's what the current day climate catastrophists do. We see that there's a period of time in the early atmosphere in the Earth when the atmosphere was comprised methane and carbon dioxide and ammonia. That changed to a carbon dioxide-rich atmosphere, and we are now enjoying in yellow an oxygen-rich atmosphere. We've had a change over time. We've had ice ages appear. The 2 vertical lines I'll go into in a minute, and we've had a number of oxygenation events tied into climate. So climate has been important for the evolution of the planet, and the warmer the climate, the better it has been. On the top left diagram, the lower layer of rocks is debris left behind by retreating ice. The upper layer is material deposited when water temperatures were only about 40 degrees Celsius. That's a climate change. And the bottom one shows some of the debris left behind, but the right diagram is the one that interests me. Those buff-coloured rocks are a rock called dolomite. That is a calcium magnesium carbonate with 48% carbon dioxide in that solid rock. Now, we can make dolomite in the laboratory. Easy to do. All you've got to do is have an atmosphere very, very rich in carbon dioxide. So this is natural sequestration of carbon dioxide. We can just measure the sequence of those rocks, walk them out for miles, and back calculate how much carbon dioxide was in the planet. That proxy is a pretty good way of working out that we had massive ice ages when the atmosphere had a very, very high carbon dioxide content. And after this great ice age, sea level rose only by 1,500 metres, covered the continents, and life evolved into complex multicellular life. And we were told that this process took place and left behind multicellular fossils, and that was meant to be the Ediacaran fauna. And about 10 years ago, this was found by a former student of mine. A new reef system, much, much older than the first complex life we thought we had on Earth. Science is never settled. It can't be. And after this life, it then got cold again. And what happened? Well, sea level dropped, just a modest 1,500 metres. Bottom layer is debris left behind by ice. Top layer is very warm water precipitates of dolomite. Again, a total planetary change of maybe 60 or 80 degrees Celsius. And after that, when the ice melted and sea level went up another 1,500 metres, we had the Ediacaran fauna appear. And these were chordates. Some of them were chordates. These are your ancestors. And some of them, and when I look around the room, it's quite likely they were, because a lot of this was green slime. And these were your ancestors. They were driven by climate change. And it's only when sea levels rose and when it became warm that we got complex life. It diversified even more into an explosion of life. It wasn't really an explosion of life, it was an explosion of predation, where animals had shells and skeletons that had sucked carbon dioxide out of the atmosphere, and they went on the rampage, and they went eating the Ediacaran fauna. They completely wiped them out. This explosion of life took place over about 25 million years. It gave us reefs. Now, we've had reefs on planet Earth for only about 3,000 million years. Reefs come, reefs go. There's nothing special about a reef disappearing. Normally they disappear when sea level drops. More of that later. And adding to a little bit of what Patrick spoke about this morning, as soon as we had life, predation, protection and warm waters, life just expanded. And we had a huge explosion of life. And it is still expanding. We are gaining more species now than we are losing. We are losing species that you can see, big things, but some of these big animals are not very cuddly. So any paleontologist will show you life on Earth is expanding, and we have our extinctions. We've had major mass extinctions and minor mass extinctions. And there are 5 major mass extinctions of complex life and over 20 minor mass extinctions. We also have species turnover. And species appear on planet Earth, then they disappear. This is the normal species turnover. That's not an extinction event. And these extinction events, we've got them very well documented. They didn't happen instantaneously. They happened over a period of time. But we lost huge families and genera and species during a mass extinction event. We can argue about the origin of these, but we are not in an extinction event, much as we'd like some of our fellow humans to go extinct. But we are in a period of normal species turnover, and the number of species is increasing. But there's some intriguing work that's coming out, and this is from looking at a very common mineral and the trace elements in this iron sulfide, which are a proxy for the amount of oxygen in the ocean waters. And we see that we've got 4 of the mass extinction events, and perhaps 5 of them, of complex life, were when we had a very low oxygen content in the water. Now, the oxygen cycle is basically the opposite of that of the carbon dioxide cycle. That oxygen depletion may well be due to asteroid impacting or massive volcanicity, but we can now start to put together cycles of oxygen. You cannot only talk about the carbon cycle, you have to also talk about the oxygen cycle. But this is quite intriguing, where we are seeing events occur that are related to changes in the atmosphere. But one of the points I want to stress today is tectonics. We know that the continents are moving apart. We know they're stitching back together again. And what's that doing? That's when we're pulling apart the continents, we are adding heat to the oceans. We are adding submarine volcanic rocks to the ocean. They spew out at 1200 degrees Celsius. They get cooled by ocean water. We only have 3.4 million recognised submarine volcanoes and 28,000 kilometres of volcanic activity along the mid-eastern rise. The East Pacific rise. So we are adding a huge amount of heat to the planet from deep down. My very first job was to work underground. When you're a mile underground, it is hot. That heat goes up in the crust. In rocks that are rich in uranium or thorium or potassium, they are even hotter. We have a very thin crust on the ocean floor. We are putting a lot of heat into the oceans. We are also adding volcanic rocks, and when we do experiments with these volcanic rocks, we can dissolve 15% by weight carbon dioxide in those volcanic rocks. So when we talk about climate, we tend to look up in the air and look at the atmosphere. Look down at your feet also. So we have very good quantitative evidence on what's happening with seafloor spreading. When we collide continents together, we actually change the way ocean currents work. When we put sediments into the ocean, we change sea levels. When we have a massive volcanic rock enter the ocean floor, we push up sea levels. Higher sea levels and covering continents with water has in the past moderated climate. So when we look at a couple of models, and you don't need to ask me my opinion on models are models, the only takeaway message from this is that as you start to shift continents around, you are changing ocean currents. And as you're changing ocean currents, you are changing the amount of heat that you transport in ocean currents. When you have a big blockage, you'll change the direction of an ocean current. So continents moving, and they still are changing the way in which we distribute heat. And one of the best examples is the breakup of the supercontinent Gondwana. And once India joined Asia, we started to get the Tibetan Plateau, change a lot of airflow on the planet, but we also started to cool down the planet. And that's when we had the beginning of the current ice age that we are enjoying. This is the key map of heat flow. This is how much heat is coming out from down below. I've been underground in South African mines, 14,000 feet underground, where you have to wear a refrigerated suit, otherwise you die. We are on the continents releasing a lot of heat, but 70% of this planet is covered by oceans. Most of the heat is being released from the oceans, along the mid-ocean ridges, along hotspots, and there is quite a bit of evidence out there showing that seismic action in the mid-ocean ridges, if you can relate that to planetary alignments, to the lunar alignments, that this is often a trigger for the rise of molten rock or for earthquakes. And in fact, the last 3 major earthquakes in the world and volcanic eruptions were at a time of full moon. So we don't understand what's happening, but we do know that some of the moons of our outer planets are needed from gravitational forces, and we suspect that a lot of carbon dioxide and volcanic rocks are released deep in the oceans when we have needing forces going on. So we've mentioned about the plate tectonics, but we haven't mentioned about weathering. I'll go into a diagram on that in a second. And the breakup of continents. Now, one of the key continental areas that's breaking up at present is Antarctica. And in Antarctica, there is a massive rift zone underneath the ice. We know of Antarctic volcanoes beneath the ice and above the ice, like Mount Erebus. We also have about 150 areas of hot rock sitting underneath that ice in Antarctica. So just because Antarctic ice is melting doesn't mean it's due to the air temperature. It could be due to other reasons. We know that when we have a pulling apart of the continent to give us seafloor spreading, that we release carbon dioxide into the atmosphere. And most of the carbon dioxide that goes into the atmosphere, it doesn't end up in plants or coal or critters. It actually ends up in soils. And those soils end up getting washed into the oceans, and the oceans then are a wonderful repository of chemicals for the precipitation of carbonates on the ocean floor. We are actively removing carbon dioxide from the atmosphere. We have for a very long period of time, and we are getting to a very critical situation in our planet. Now, these are some of the examples of old Great Barrier Reefs. Left-hand photograph, that is a Great Barrier Reef inland about 300 kilometres from the current Great Barrier Reef. The 2 photographs on the right are a Great Barrier Reef in Western Australia. And you can calculate from the bottom photograph, you see those limestones just going off forever. That rock's got 44% carbon dioxide in it. You can just measure the thickness of it and work out the depth of it from geophysics and work out how much carbon dioxide had come from the atmosphere to give you those rocks. We are constantly sequestering carbon dioxide into soils, into life, into the oceans, and this is a process which cannot be changed. But we are putting a lot of material into the atmosphere also. Any molten rock has dissolved gas. On one of the tables out there's a wonderful granite that was molten with a very high proportion of vapour in it. These granites here released vapour into the atmosphere as they were rising. When we have volcanoes, they release gas as they rise, not when they erupt, but before the eruption. These are volcanoes in East Africa composed of carbonates. These are sodium, calcium and magnesium carbonates. These volcanic carbonate rocks are the ones we mine for rare earth elements. We understand them quite well. These carbonates have got at least 40% carbon dioxide coming from deep down in the earth. The earth is still degassing. We see that with every rock that was once molten. We also have gas volcanoes. These are a place in Takta Suleiman in northwestern Iran. And these were volcanoes composed only of gas. And that gas was carbon dioxide. Also in Iran, we know from measurements of earthquakes that as soon as you break the earth, you release huge amounts of gas, in this case water vapour and carbon dioxide, into the atmosphere. So we are constantly degassing planet Earth. Every time you push up mountains, you degas the planet, mainly water vapour and carbon dioxide. The hot springs in these mountains are bicarbonate hot springs. But this is a diagram that Patrick showed earlier, and this is showing us just the last 20% of time, where we can see in purple, carbon dioxide is up and down like a yo-yo, but the general trend is down. The temperature is up and down, and we have recorded the ice ages there, and this is telling us that the planet's carbon dioxide content is decreasing. If we halved the amount of carbon dioxide in the air today, we would have no plant life, and hence we'd have no animal life. It is not a crisis of climate. It's a crisis of common sense that we face. It's not a crisis of climate, it's a crisis of using data. It's not a crisis of climate, it's a crisis of carbon dioxide. We don't have enough of it. And whatever we can do, making cement, making steel, put more into the atmosphere. You are saving the planet by doing that. We see in the past that the oceans have warmed and cooled, and we have proxies. The bottom one there is just from some oxygen isotopes and carbon isotopes in planktonic organisms. Ocean surface temperatures up and down over the past. Just because it's gone up in your lifetime doesn't mean that you've had anything to do with it. So we see from the surface of the oceans and the fossils that come from the surface of the ocean that the surface of the ocean is very, very sensitive to temperature. This is ice core data showing the last 5 glaciations within our ice age, and you'll note on the far right, it's not very warm compared with previous interglacials. We've had temperature rises and falls extraordinarily rapid and extraordinarily intense. I really hate to depress you, but you're not living in exciting times. You're living in very boring times. There's nothing much happening on the planet. We hear these horror stories about sea level changes and how sea level's going to inundate all these Pacific atoll island nations. Well, we know from the past sea level's gone up and down by 1,500 metres. Our current sea level has risen in the last 14,500 years about 130 metres. Sea level has actually gone down in the last 6,000 years because we've come out of the peak of our interglacial. So sea levels go up and down, but you never hear about land levels going up and down. These are some satellite photographs of Pacific Island atolls showing that since we've had satellites, what's happened to the atolls? They've got bigger. Well, we should know that because Charles Darwin wrote a book on coral atolls and coral reefs in 1842. And he picked up an idea of Charles Lyell from 1833. And Darwin argued that we had sea level with a coral atoll sitting on top of a volcano, and as sea level rose, or as we had a falling of the volcano, then we basically had the atoll continue to grow. Charles Darwin proved that in 1842. It was validated by drilling of coral atolls for the nuclear testing in the 1950s. We have known for a very long period of time that if sea level rises, the coral says thank you very much, and it just grows and grows and grows. And this is a complicated, busy diagram showing in blue the sea level rise, and in green, the temperature change. There is a rough correlation, but what is interesting is that in the far right of the diagram, we've got various great periods of time. And the great empires existed on planet Earth when it was warm and when we had high sea levels. Warm weather doesn't kill you. It's the cold weather that kills you. This is why we've had stories about Jack Frost for a long, long time. So sea level rises are quite normal. So is land level rise. This is in northern Norway. We had Scandinavia under a few kilometres of ice. That ice is gone. Scandinavia has risen. And these are old beaches, up to 340 metres above sea level. So we're quite comfortable with the sea levels rising and falling, but what about the land levels? Some of you might have been to the port of Ephesus, mentioned in the Bible. That's 15 kilometres inland, 7 metres above sea level. What's happened? The land's gone up. Nearby is the ancient city of Lydia. I've been down the main street of Lydia in a yacht. And so, obviously, the land level's fallen. This is taken in the Great Barrier Reef, and there's a layer there of shelly material about 2 metres above the current sea level. And that has been dated. That material grew in the Holocene optimum about 4,000 years ago. The chap with his hat on is Bob Carter, who had performed at some of these conferences before, the late Bob Carter. This is showing us that land level has either risen or sea level has fallen. In this case, it's sea level that's fallen. These are micro-atolls which have died. This is a fresh micro-atoll. This is what happens to the coral micro-atolls when sea level changes. When you expose coral, it dies. That's got nothing to do with humans. That's natural events. So we know from looking at the past that there are natural cycles. And these are the pulling apart of continents, the pushing back together of continents, having a bad galactic address and getting covered in ice, having the orbit of the Earth change, having the sun put out variable amounts of energy and lunar tidal nodes. We have cycles of climate, and when some of them coincide, you will get a fairly rapid climate change. And just to finish off, what does the past tell us? Well, it tells us that we're living in boring times, that we have water and the air and rocks and life all working together. Nothing has changed since those iron formations formed. Climate change is quite normal. Massive climate changes, very rapid climate changes. Humans have survived. We have had climate change ever since the first day on this planet, and for most of time it's been warmer and wetter than now. For most of time sea level's been higher than now. We are living in those sort of extraordinary times. We seem to forget that carbon dioxide is the food of life. It's plant life. Most of the world's carbon dioxide doesn't end up in the forests or the grasslands or the rangeland or in crops. It ends up in algae. We don't see it. It doesn't get measured very much. So my story is that we don't measure what's beneath our feet. We don't really know what's going on in the oceans. We have some very good clues that oceanic heat and carbon dioxide is greatly underestimated. We also see cycles of climate and accidental events, such as dirty big volcanoes or an asteroid impact, which have an effect on climate. Now, if you can't read this, it doesn't matter. If you can't read it and you're colourblind, you've got real problems. The argument I'm putting up here is, in our current interglacial, and they last for about 10,000 years, and we're now overdue. We've been cooling for a few thousand years. If you just look at the periods of cooling and warming in this last interglacial, we are in the period of modern warming. What do you think the next colour is going to be? Thank you.
Então, pontos importantes vistos. Nosso clima atual é chato. Climas do passado, sim, esses foram extremos. Portanto, qualquer evento não é nada quando comparado aos do passado. Ele fez bem essa colocação. 3 dias de calor, estamos morrendo. Veja só, né? Temperaturas de mais de 40 graus, inclusive na água. Tá? Então, temperaturas foram muito mais elevadas no passado e o CO2 era baixo. Quem fez a videoaula já viu aquele gráfico que ele mostra na apresentação, muito bem explanado, para quem fez a videoaula, né? Tá? Que o nosso tempo atual, o Holoceno, foi quente há aproximadamente 12 mil anos atrás e é frio hoje. Então, esses caras estão falando de aquecimento agora, ridículo, foi frio perto do que foi no passado, 12 mil anos atrás. E tivemos concentrações absurdas de CO2 e a Terra era um sorvete em todas as eras glaciais. Ele mostra isso, tá? Que as rochas e os oceanos, isso eu achei sensacional, são enormes absorvedores e emissores de CO2, incomparavelmente maiores que qualquer coisa que os humanos façam. Fala também do nível do mar e as regressões e transgressões marinhas, coisas que a gente acabou de mostrar num vídeo recente, com fartos exemplos, incluindo as formações de corais, né? Acredito que você nem imaginava que isso aí poderia ser uma verdade, uma realidade, né? Principal, a Terra ainda está se desgaseificando, adorei essa palavra, ou seja, as rochas estão a soltar muitos gases na atmosfera. E os ridículos como o Klaus Chupeta e as seclas associados dizendo que são as vacas, né, pessoal? É isso daí. Então o vulcão está soltando um punzão planetário, né? E o pessoal está aí todo melindroso, né? Fontes de calor por baixo dos oceanos, ele mostrou um gráfico sensacional mostrando quanto de calor está vindo de baixo e da Antártica, que devem ser consideradas também, né? E eu gostei muito a riqueza das rochas, né? A concentração de CO2 e de oxigênio que está aí nas rochas, os silicatos, como a gente mostra nos processos de siderurgia, né? A escória sobe, os metais descem, então a gente vê que os gases estão lá presentes nas rochas. Não podemos esquecer nunca disso daí. Eu gosto muito de falar aqui do filósofo Leibniz, né, que eu falei para vocês que estudava tudo, aquele cara era sensacional, inclusive foi ele que observa lá, né, o processo de siderurgia, ele falou, o planeta Terra deve ser semelhante, então a gente mora na escória do planeta Terra, na crosta, nas rochas, né, onde solidificou, que é muito pouco em relação ao planeta todo. Você vê isso no nosso curso Bases Científicas e Epistemológicas, a gente mostra as relações escalares. E, finalmente, o ego inflado dos seres humanos, aqueles que são corruptos e trabalham para uma agenda diabólica, estão a afirmar que nós conseguimos mudar o clima do planeta. É muita soberba, né? Bom, vamos lá, lembrando para vocês que nós estamos aí, então, que já está disponível o lote 1 do nosso grande projeto Mudanças Climáticas, Geopolítica e a Guerra Espiritual, né? O curso Bases Científicas e Epistemológicas contra a Fraude da Mudança Climática. É a parte 1B, né, que faz aí o complemento à parte 1A da nossa videoaula. Então, esse curso já está disponível para você adquirir aí através desse link, deixando sempre o pessoalzinho nervosinho, né? A Greta Fonda vai ficar muito nervosinha. Lembrando que nós montamos um canal no Telegram, né, um recado importante, canal Master Ricardo Augusto Felício, para você ter lá todos os backups. Agradecimento aos nossos queridos apoiadores, ao pessoal da Vaquinha, o Everaldo, a Lígia e a Silvia, meu muito obrigado. Estamos sempre orando por todos vocês que nos ajudam aqui no canal, o senhor Rubens no PayPal, os queridos amigos Celso, Marina e Maria, que fazem contribuições no Caixa ou nas lotéricas, e aos nossos grandes heróis, nossos 20 apoiadores, que estão lá firme e forte, sempre nos ajudando aqui no canal. E, é claro, aos nossos grandes colegas que nos trazem aí sempre alguma sugestão. Eu espero que vocês tenham gostado bastante do nosso vídeo de hoje e dessa apresentação fabulosa do geólogo, professor doutor PhD Ian Plimer. Um grande abraço para todos, fiquem com Deus e até o nosso próximo vídeo, pessoal. Até lá!